Okay, so this video is going to be all about tape diagrams. Tape diagrams are sometimes called bar diagrams because they look like bars. And they can be used for a variety of reasons and for a variety of levels, which is really nice. So I'm going to show you just a basic one that you might see in elementary school. So if I had a bar or a tape, kind of strip of tape with 3, 3, 3, 3, I could then see that that equals 3 plus 3 or 12. Or I could also say I have 4 times 3 and to get 12. So it's just a nice visual for kids who are more visual learners. You could also kind of step that up a notch and do X. And then that equals 12. So then you would say 4X equals 12, and you would have a visual to see that you would need 3 in each section of your tape or your bar diagram. So X equals 3. And it's a nice visual to show kind of the meaning of division, that you're going to divide this 12 into equal groups. Okay, let's step it up a little bit more. So you could have a 2-step equation. So you could even start with a tape diagram and have kids create an equation from that. So if I had X 12 and then 20. So notice this kind of has that double bar diagram instead of just showing it's the answer underneath. You could have a whole separate tape. So in this case, I would see that I have 2 X's plus 12, and that I would need the whole thing to equal 20. So then this is a nice visual to show that this must be 8, because I know 8 plus 12 is 20. So if I have these 2 X's that need to equal 8, each one must be 4. And this is a nice way, a nice visual to kind of show where some of these inverse operations are coming from. So notice how I got the 8 was really 20 minus 12. So I really needed to subtract 12 from both sides. And then I was left with 2 X's equal to 8. And then if I divided those 8s into equal groups, I would get 4 and 4. So you could either start with the equation and have kids make the bar or tape diagram, or you could start with the tape diagram and have them make the equation and solve. You can kind of go either way with those, which is really nice. You can also do fractions. This is probably one of the most familiar uses of tape diagrams, kind of to show those equivalent fractions. So if I had, that is not evenly split, but if I had 3/4 and then I had 8s, I would see that 3/4 and 6/8 are equivalent from my bar or tape diagram. Sometimes they're nice for story problems, because story problems can be tricky, and to kind of have a visual to go with them is really nice. So here is a story problem that I think I took from a 4th grade text, but could easily kind of be adapted to a higher level. So Simon threw a big party on New Year's Eve. He bought 5 boxes of hats with 12 party hats in each box. He split the hats evenly among 3 baskets and put them out for his guests to take. How many hats were in each basket? So first I'm going to start out with my 5 boxes. So I'm going to kind of create my tape diagram with my 5 boxes. And I know it says that there are 12 hats in each box. But then I'm going to take those 12 hats and put them into 3 baskets. So I need to kind of see how these 12 hats are going to get split into 3. So this helps me really visualize that I have this total amount of hats, which ends up being 60. So if I have 60 hats, and I can kind of put that down here as well. If I have 60 hats that I need to now split evenly amongst 3 boxes, so I could say 3x equals 60, or it's just such a nice visual, kids might automatically know that it's going to be 20, 20, 20. And you could then double check it, or have them check it. 20 times 3 gives me 60, and 12 times 5 gives me 60. So those are going to be even, and those are going to be the total amount of hats. Okay, you could also extend it to a 7th grade equation solving problem. So if I had the following equation, 3 times the quantity of x plus 2 plus 7 equals 40, I could create a tape diagram to match that equation and give it a more visual. So I know my total is 40. And then I have these 3 boxes of x plus 2. And then I have this extra 7 kind of hanging out there. So visually, I can now see that I have these unknown amounts that must equal 33, because I know 33 plus 7 equals 40. But if I was solving with my rules of inverse operations, my first step would have been, well, I'd have a couple options. I could have done the distributive property, or I could have gotten rid of this 7. And then I would have been left with 3 quantity x plus 2 equals 33, which is what my visual shows up here, is I have these 33 kind of unknown boxes. So now that I know I have these 3 unknown boxes to equal 33, I can use that to know that each box must be 11. So 11, 11, 11. Because I know that 3 times 11, if I was looking at a multiplication chart or multiplication table, 3 times 11 is 33. So knowing that each of those is 11, I could then say, and even in my equation, dividing both sides by 3, x plus 2 equals 11. And so with x plus 2 equal to 11, I know that 9 plus 2 equals 11. So therefore, x must be 9. 9 plus 2 equals 11. And then I can double check it at the end. I could rewrite my tape diagram and do 9 plus 2, 9 plus 2, 9 plus 2, and then 7. And then I could even simplify it, 11, 11, 11, 7, and check that that gives me my total of 40 that I had. And it does. 11, 22, 33, 7 does equal 40. So it's a nice visual to kind of tie into equation solving or equivalent fractions, or just creating a visual for a story problem like the New Year's Eve hats. So those are various ways to use tape diagrams or bar diagrams, they're often called as well.